Hey everybody, and welcome to a video on conditional probability. Last week, we introduced the basics of unconditional probability theory. This theory gave us a way to assign epistemic probabilities to certain statements, namely tautologies, which we know get probability 1, and contradictions, which we know get probability 0, and also a way to assign such probabilities to certain other statements given the probabilities of logically related statements. For example, we know that if P and Q are two logically equivalent statements, then they have to get the same probability. And that probability of not P, or any proposition P, has to be 1 minus the probability of P, and so on. Probability theory really starts to get interesting, though, once we introduce the notion of conditional probability. And that's what we'll do in this video. Well, we've been interpreting unconditional probability thus far as epistemic probability, right? The probability that you assign to particular propositions, how likely you think they are. Conditional probability may be interpreted as a formalization of the notion of inductive probability that we started out the class with. Right? Now recall, right, that notion of inductive probability. Right? If we had an argument that had some premises, x1, x2, notice how many premises we have, go down, and then terminates in the conclusion that y is the case. Right? We said that the inductive probability of this argument is informally, right, a measure of how likely the conclusion y is to be true given the truth of the premises. Right? Now, if we wanted to write the epistemic probability of y, say, right, we would write it like epistemic probability, right? Write it like P, and then y in parentheses, right? The probability of y. But if we want to capture the inductive probability of this argument, unconditional probability won't do, right? For example, right, it wouldn't work to write, say, right, so here we want to capture the inductive probability of the argument, right? It's not going to work to write, for example, something like the probability of y and all of these premises, right? Y and x1 and x2, so on, right? Right. This will give us a measure of how likely all of the statements that appear in the argument are to be true, but not a good measure of the inferential link between the argument's premises and its conclusion, which is what we want the notion of inductive probability to capture, right? So think of an example here, maybe, right? Maybe we have a premise that ogres live in swamps, and then we conclude from this that swamps are dangerous, right? Here, right, let's suppose you think that ogres are very dangerous creatures, then you would want this argument to have high inductive probability, right? It would be likely that swamps are in fact dangerous given the premise that ogres live in swamps, right? But, right, the conjunction, right, the probability of both of these, I'll call the first proposition x, and I'll call the conclusion y, well, probably the conjunction of x and y is very low, right? Because it's very unlikely that ogres live in swamps, since it's very unlikely that ogres exist, right? And yet, the inductive probability of the argument is high. Right? Inductive probability is high, right? Because the conclusion is likely to be true given the truth of the premise. Given that ogres really live in swamps, then swamps may be dangerous. So inductive probability of an argument is not just the epistemic probability of the conjunction of all the statements appearing in that argument. So the premises of an argument might be unlikely, but that's not what we're trying to capture when we measure inductive probability. Rather, we want to measure how likely the premises would render the conclusion if we were to just assume that the premises were true. So we'll use conditional probability to capture this notion. Now, whereas unconditional probability was a one-place function, assigning real numbers to propositions, remember how we set that up, where we assumed, right, in the setup that we had, right, a set S of simple statements that we were attaching probabilities to. But we weren't just attaching probabilities to statements in S, we were also attaching propositions to we called A parentheses S, or right, the algebra, logical algebra generated by S. Right? And this just meant that we weren't just considering simple statements, but we were considering any propositions you could form using simple statements in S and the logical connectives with which we're familiar, not, or, and. Right? So then probability, right, remember, right, unconditional probability was just a one-place function, right, from our algebra of propositions to the real numbers, right? And it tracked likelihood, right? In the sense that, right, for any propositions x and y, the probability of x was greater than the probability of y, just in case x is more likely than y. Right? Now, conditional probability has to be a two-place function, right? That is to say, right, we could really think of it, it's a function from ordered pairs of statements in our algebra of statements to real numbers, right? And it has the feature, right, that it's tracking conditional likelihood. So, probability of x given y will be greater than the probability of, let's say, A given B, just in case x is more likely given y than A is given B. Okay? So conditional probability is now a measure of conditional likelihood. And we write it as I wrote it up here, right? So, right, probability, the conditional probability of a proposition A given B is written as P open parentheses A, and then we use a line, a straight line, to represent conditional upon or given B, the event where. So, for example, if we had that argument started, example, if we had that argument started with x1, went to x2, right, so on, to the conclusion that y, we could write out the inductive probability of this argument using conditional probability as the probability of the conclusion y given the conjunction of all of the premises, x1 and x2 and so on. Right? That would be how we would cash out the inductive probability of this argument. Okay. Now, what I want to do is connect conditional probability with unconditional probability in the standard way. And you could think of this as, in effect, adding a fourth axiom to our set of probability axioms, and we call it the ratio rule. All right. This is super important, so maybe I'll box it. Right? And this says that if the probability, unconditional probability, of a particular proposition is non-zero, so it does not equal 0, then we can relate conditional and unconditional probability in the following way. The probability of any proposition A given B will just be equal to the probability of the conjunction A and B over the unconditional probability of B. Right? So this now connects conditional probability on the left side of the equality here with a pair of unconditional probabilities on the right side. Right? So if we know some information about unconditional probabilities, we can figure out conditional probabilities. All right, this rule will be central to us as we go forward. Now, I want to point out a few different consequences of this rule in conjunction with our axioms of probability, and these will be handy things to note as we go forward in terms of solving problems on homeworks and exams and such. So the first thing I want to point out is a simple proposition that if B entails A, right, that is to say, we have a deductively valid argument from starting with B as a premise and concluding with A. Right? Then the probability of A given B is 1, right? And this is what we'd want to have because, right, this probability of A given B is, right, measuring the strength of an argument from B to A. And if B actually entails A, that is if we have a deductively valid argument from B to A, then we would want it to have maximal strength, right? We'd want it to get probability 1. So this is what we would want to have happen. Let's show that this does indeed happen, right? Well, let B entail A. B is some proposition that entails A. Then we know that the probability of A given B is equal to, by the ratio rule, the probability of A and B over the probability of B. Now note here, we do have to make an assumption. I should be explicit about this. Up here, we're going to assume that probability B is not equal to 0. Right? So throughout, we're typically going to assume that the events that we're conditioning on, or supposing to be true, are not events that we think have minimal probability attached to them. Okay. All right, so given that, we can use the ratio rule here. So now note that that A and B, though, is logically equivalent to B in the case when B entails A, right? And we could use a truth table to show that if we wanted to. And so this results then in probability of B, right? This is by the logical equivalence rule. Since A and B is logically equivalent to just B, we can substitute in B. It's probability of B over B, but that, of course, is just 1. So now we get the probability of A given B is 1 whenever B entails A. All right. So that's the first simple thing to note. Next thing we want to note, which is sort of related, is that if B entails not A, so if B guarantees that A is not true, B entails not A, then the probability of A given B is 0, right? And this again is what we would want, right? Because the probability of A given B is measuring the inductive strength of an argument from B to A. And if we know that B guarantees the truth of not A, then we would want an argument from B to A to get to get measured as having minimal strength. It'd be the weakest sort of argument you could have here. Right? So let's show that this is true. So again, let B entail not A this time. Right? Now let's work out what the probability of A given B is. And of course, I'm making the same assumption that the probability of B is not equal to 0. Right? Oh, let's see. I miswrote that up there. Yeah, the probability of B is not equal to 0. Okay, so by the ratio rule then, we know this is probability of A and B over probability of B. All right. Now, since B entails not A, that means that A and B is a contradiction, right, by propositional logic. So that really means that we have probability of, right, a contradiction up here. And since A and B, maybe I'll write it like this. I'll say, since A and B is a contradiction, it has to have 0 probability. Probability of A and B is equal to 0. But then, probability of A given B is equal to 0 over probability of B. We know probability of B, I'm assuming, is not 0, so this whole thing then is 0, which is exactly what we wanted to show. Cool. I'll put that up here too. All right. Okay, the next thing I want to show, I want to consider what happens if we condition on tautologies. Okay. So if we condition on a tautology, right, I claim that for any proposition A, the probability of A conditional on a tautology is just equal to its unconditional probability, right? And this is sort of what we'd want to have, right? An argument that starts with a tautology as a premise and moves to A, that's just going to be sort of as good as whatever we think the prior likelihood of A is, right? Using a tautology as a premise doesn't really help you very much in an argument because you always have tautologies to rely on. Tautologies are always true. So let's show that this is true. Proof. We let A be a proposition. Then by the ratio rule, we know the probability of A given a tautology is equal to the probability of A and a tautology over the probability of a tautology. And here we don't have to worry about tautology having 0 probability because our axioms say tautologies always have 1 probability. Right? So this then is equal to, right, we know the probability of A and the tautology, right, is just probability of A by logical equivalence, since any proposition conjuncted with a tautology is just equivalent to itself. So this is then probability of A over probability of the tautology. But as we said, probability of tautology is 1. So this is just probability of A divided by 1, which is probability of A. Right? So learning or conditioning upon a tautology doesn't change the probability of any proposition, right? Which is what we would sort of antecedently expect. Right? That's what we would want to be the case. All right, next claim I want to make is that conditional probabilities, right, or probability conditional upon any fixed proposition is a probability function, right? It's going to satisfy the probability axioms, right? So I'll say for any fixed proposition x, probability given x is a probability function. And by that I mean it satisfies those Kolmogorov axioms we talked about in a previous video. So this is what we'd want to have happen, but let's make sure it does. So what's required for it to be a probability function? Well, let's remember there's those 3 axioms, right? First of all, the tautology has to have probability 1. So let's make sure that the tautology has probability 1. Well, probability of a tautology conditional upon x by the ratio rule. Again, I'm assuming here probability x is not a doesn't have 0 probability attached to it. So this is going to be equal to probability of t and x over probability of x. Right? Now, right, a tautology and x, right, is just the logical equivalent to x, right? So we get probability of x over probability of x, right, substituting in by our logical equivalence rule, and any number divided by itself is just 1, right? So now we know that this conditional probability function, conditional upon x, assigns 1 to a tautology, which is exactly what we wanted. Now let's check for non-negativity. Let's make sure it never assigns negative numbers to anything. So, right, let's let A be some arbitrary proposition. We want to make sure the probability of A given x is non-negative. Well, we know by the ratio rule, it's equal to the probability of A and x over probability of x, but, right, the non-negativity axiom for unconditional probability guarantees that we're taking a positive number, right, or a non-negative number, and dividing it by another non-negative number, right? And that's going to result in a number that is itself non-negative, right? So greater than or equal to 0. So we check that non-negativity holds. Now just to make sure that additivity holds, right? So let's let A and B be mutually exclusive propositions. So be mutually exclusive, right? That means that their conjunction is a contradiction. exclusive. Now we want to show that the probability of A or B given X is equal to the probability of A given X plus the probability of B given X. So let's show that this is indeed the case. This is what we want to show. Well, we know that the probability of A or B given X has to equal the probability of A or B and X divided by the probability of X by the ratio rule. Right? Now, we can use some propositional logic to show that A or B and X is really logically equivalent to A and X or B and X. Right? And we could use truth tables to show that. So by the logical equivalence rule, that has to get the same probability, right? Divided by probability of X. Okay? Now, right, we note that A and X and B and X have to be mutually exclusive with each other, right? That is, their conjunction has to be a contradiction, since it entails the conjunction of A and B, which we know to be a contradiction. So that means that up here on the numerator, we can apply additivity of unconditional probabilities and get probability of A and X plus probability of B and X. Right? Divide the whole thing by probability of X. Right? Or we can now just separate out this fraction, right? We get probability of A and X over probability of X plus probability of B and X over probability of X. But now, right, by the ratio rule, this is just the same thing as the probability of A given X plus the probability of B given X, which is exactly what we wanted to show, that additivity holds for conditional probability upon a fixed proposition. So now we've shown that if we fix a particular proposition as the event we're conditioning on, conditional probability is probability, right? Satisfies the probability axioms. Okay, the next rule or proposition I want to point out is a handy rule that will help us in some problems going forward. And that is what we'll call the general conjunction rule. And this gives us a rule for how to find the probability of the conjunction of propositions. So, according to this rule, the probability of a conjunction of propositions, A and B, is equal to the probability of A given B times the probability of A. Excuse me, of B, right? The event that we're conditioning upon. All right, so if I know the probability of A given B, and I know the probability of B, then I can multiply them to find the probability of the conjunction of A and B. And this follows actually just immediately from the definition we had of conditional probability, or what I should perhaps more appropriately just say, the ratio rule that we had, right? So if we wanted to do a really simple proof here, right, we know that the probability of A given B, right, again, assuming probability of B is not 0, is equal to the probability of A and B over the probability of B, right? Now we just multiply both sides by probability of B, so we get the general disjunction rule. Probability of A and B equals the probability of A given B times the probability of B. That's one that will be very handy going forward. All right, now the last thing I want to do in this video is I want to connect this notion of conditional probability with the notion we discussed earlier when we talked about the gambler's fallacy. And that's the notion of independence, or what we sometimes call probabilistic independence or evidential independence. And this is a relation that holds between propositions, right? So, independence. Now remember, in the context of the video on the gambler's fallacy, we said that A and B were independent if the argument from A to B, right, it's an argument that had A as a premise and moved to B as a conclusion, was just as good as the argument that started with not A as a premise and then moved to B as a conclusion. Right? If these were sort of equally good arguments, then we said A and B were independent. Now we can state this in terms of conditional probability, though. So this will be a definition. We'll say that propositions A and B are independent of one another if the probability of A given B is equal to the probability of A given not B. Right? That is right. An argument starts as B, moves to A as a conclusion, or an argument that starts from not B, moves to A as a conclusion, are both equally good arguments. Right? Now, if this holds, if this equality holds, then it's actually also going to be the case that the probability of A given B is just equal to the probability of A. Right? Learning B, or conditioning upon B, doesn't change the probability of A. Right? Now, to show that this equality here follows from the equality on the left would actually be a good homework exercise to do. So maybe I'll put that in the homework. But this is the definition then of what it is for events to be independent. Now, one thing I want to point out is that independence is like mutual exclusivity in the sense that it's a relation that holds between different pairs of propositions, right? So A and B might be independent with each other, or A and B might be mutually exclusive with each other if A and B are statements, right? But the sort of relation that independence constitutes and the sort of relation that mutual exclusivity constitutes are very different, right? You should keep those notions very distinct there. It's often, I think, gets tricky in probability classes or statistics classes when you first learn about independence and mutual exclusivity. Sometimes students will mix them up with each other. But these are very different notions, right? Remember, mutual exclusivity, right? A and B are mutually exclusive if, right, their conjunction, right, is a contradiction, right? A and B can't both be true, right? And that means, right, that the probability of their conjunction, all right, using the same notation we've been doing, A and B is contradiction. That means the probability of their conjunction has to be 0, right? Whenever they're mutually exclusive, right? Independence is a different game, right? They're independent, right? Just in case this condition up here, we'll say A and B are independent, right? If probability of A equals probability of A given B, right? So learning B doesn't tell you anything about the probability of A. In general, right, mutually exclusive propositions are going to tend to not be independent with each other, right? Because if two propositions are mutually exclusive, we know they can't both be true. So if I learn one of them is true, right, that tells me that the other one has to be false, right? So in general, learning one of two mutually exclusive propositions does tell you something about the other, right? The only case where that would not be the case would be if one of them is a probability 0 event. So let's say probability A we already know is false for sure, and then I learn a proposition that's mutually exclusive with it. That doesn't end up changing my probability for A. But in general, right, mutual exclusivity and independence are very, very different notions. Okay. So I just wanted to do that as an aside note. All right. So now that we have our definition of independence down, we can introduce another rule. This will also be a very handy rule for us going forward. Now I'm going to call it position 6. We'll call it the special disjunction rule, or excuse me, the special conjunction rule. Right? According to this rule, right, if propositions A and B are independent, then the probability of their conjunction, A and B, is just the product of their individual probabilities. So probability of A times probability of B, right? So in statistics, when we're assuming different propositions are independent, right, the nice thing about that is it allows us to use this rule. So it allows us to compute the probabilities of various compound events or conjunctions in a very tractable way through multiplication. So let's show quickly that this is true. It again follows pretty readily from the definition of independence and the general disjunction rule, right? So let A and B be independent, right? Then that means that the probability of A is equal to the probability of A given B, right? But we know by general disjunction rule that probability of A and B is equal to the probability of A given B times the probability of B, right? But now substituting in by the independence of A and B, we get that it's equal to the probability of A times the probability of B, which is exactly what we wanted. All right, so these will be handy rules that we'll use, as I say, in the homeworks and exams moving forward. So in the next video, we'll get some practice actually computing some simple conditional probabilities. So we'll get more intuition for how to use these rules, more intuition for what independence means. We'll see some examples using cards and such. So that'll be in the next video. So don't forget to complete the participation poll for this video, and I'll see you next time. Thanks, guys.